Welcome back, everybody. Over the last couple videos, we've been talking about the derivative, not just the derivative, but what it means. And we've said that the first derivative would equal the slope of our tangent line, right? And then we took a look at each one of those tangent lines, and we said if the slope was positive, our function would be increasing. All right, here, right, we start positive, but then we start going down, right? So, but it's still positive, so our function is both increasing in both ways. All right, so my question today is, what is our second derivative going to say about our original function? So let's take a look at the figure that I have. All right, now notice, all right, if my tangent lines are below my original curve, right, this is called concave up. We know it's concave up. The rhyme I use is concave up is like a cup, concave up. If our tangent lines are above the curve, all right, then it's concave down. And concave down is like a frown, so we have concave down. All right, so how does this concept relate to the second derivative? Well, if we notice in the first case, right, this derivative, while it's positive, is a very small number, right? This one's a larger number, this one's a larger number. So if our first derivative is increasing, meaning our rate of change is going higher, it's concave up. So if our second derivative, our rate of change, is positive, we are concave up. Now notice here, I'm going to erase these for just a second. This would be a very large number, right? This would be a very big slope. This would be a slightly smaller slope. And this would be a smaller slope, which means our rate of change is going down, which means that our second derivative is going to be a negative number. If our rate of change is decreasing, that means the slope is negative. All right, and that's concave down. And that's what we're going to explore today. All right. So let's begin with the idea. Now, when we did our first derivative, we had a thing called a critical number. All right. Critical numbers were very important because that's when it changed from increasing to decreasing, right, at that critical number. It didn't always do that, but that was the only possibility where it could. All right. With our second derivative, we're going to look at something called an inflection point. All right. An inflection point is going to be where the function changes from concave up to concave down, or vice versa, right? Right? Could change from concave down to concave up as well. All right. So, I think the best way to illustrate this is with an example, because I can talk you through what we're doing conceptually as well. And a lot of people can follow examples. Oh. All right, here is my example. If f of x equals x to the fourth minus 4x cubed, find the inflection points. So the first thing we're going to find is our first derivative. And that would be 4x cubed minus 12x squared. And if I set that equal to 0, I could find my critical numbers. All right. Now I'm going to find my second derivative. My second derivative is 12x squared minus 24x. Now the inflection points happen where the second derivative is either equal to 0 or does not exist. In this case, the second derivative exists everywhere because it's a polynomial. So we only have to say, where does our second derivative equal 0? All right, so at this point, I'm going to ask you to pause the video and find out where it equals 0. And let's get our two possible inflection points. All right, so hopefully you pause the video. And I'm going to do it real quick. So I have 12x, and I'm left with x minus 2. So I get 12x equals 0, x minus 2 equals 0, x equals 0, and x equals 2 are the two possible inflection points. I'm not saying they're guaranteed to be inflection points, but those are the only possible points of inflection that we have. Now, the reason I'm saying they're possible is because the definition of inflection point is where concavity changes. And just like with our critical numbers, all right, we don't necessarily have to have a concavity change just because we have a potential inflection point. So we do have to check, we do have to do a chart just like we did before to check for concavity. So all right. So our chart is going to be very similar to what we did before, except we're working with our second derivative. So I've got negative infinity up to 0. And it's the same idea. The only potential places where concavity can change are these two places. So if it's concave up at like negative 1,000,000, it's still going to be concave up at negative 100. Still concave up at negative 1. The only potential place, the first potential place it could change would be 0. Then 0 to 2. And then 2 to infinity. So I'm going to get some nice easy points where I can plug them in quickly. And so why don't you do this? Why don't you take those points, plug them into your second derivative. I'll scroll down like this. And remember, we don't need to know the exact number. We just need to know if it's negative or positive. All right? And we'll talk about the answers on the back end. All right. Hopefully you went through the process. I got that the sign was positive, negative, positive. Pull that up. That's a definite positive. And I got concave up, concave down, concave up, which means that both and x equals 2 are points of inflection. All right. So let's do another example, all right? But I want to start putting our first and second derivative tests together, all right, to really get at what the goal of this exercise is, because we really haven't talked about much about the overall goal, all right? And the overall goal is curve sketching. The more complicated the curve, the less likely you'll be able to do an XY table in order to get points and plot your curve. However, from the information gained from our first derivative test and second derivative test, we could sketch a graph that would be pretty close to what we need. All right, so here's the problem. Sketch the graph of the function. F of x equals x to the 2/3 times 6 minus x to the 1/3. All right. So the first thing we need to do, right? The first thing we need to do is find f prime of x and find f double prime of x. All right. So I'm going to have you do this, and I'll give you the answers on the other side. All right, so to gain our first derivative, we need to use the product rule. Now, you've done the product rule plenty of times. I'm just going to give you my answer. My answer was 4 minus x over x to the 1/3, 6 minus x to the 2/3. If your answer differs, just check to make sure, because I simplified mine as much as possible. So yours might be a similar answer. It just might be not as simplified as mine is. So be sure when you're doing this curve sketching, don't just do the first and second derivative and leave them unsimplified. The more you simplify them, the easier the next steps are going to be. All right. So to do the second derivative is two ways. First of all, you could either take the first derivative, use the quotient rule, or you can use logarithmic differentiation, which we haven't discussed yet, but if you know it, you're welcome to use it. I got -8 over x to the... let me try that again. 4/3 times 6 minus x to the 5/3. Again, same thing. You might have a correct answer, just not as simplified as me. So be sure to do that algebra, because in this form, your next steps are going to be a lot easier. All right, so the next thing we need to know is our critical numbers. All right. So to find out when f prime equals 0, right, we just use the top, right? 4 minus x, and we say 4 minus x equals 0, so x equals 4. And then I can look at the bottom and say if x equals 0, the bottom equals 0. And if x equals 6, the bottom will equal 0. And if the whole bottom equals 0, that means our first derivative does not exist. So all three of these are critical numbers. Now, a lot of textbooks, right, have you try to find everything at once. I think it's just too much. So I'm going to continue with the first derivative test until I finish, and then I'm going to go to the next one. So I have interval, test, sign, conclusion. So for my interval, I need -infinity up to 0. I need 0 to 4. I need 4 to 6. And then I need 6 to infinity. So the more critical numbers you have, right, the more intervals we're going to need. So I'm going to put in -1 as my test point, 1, 5, 7. Now, in reality, any point in that interval will work fine. But I'm picking numbers that just are easy for me that I can plug these into my first derivative, which is up here, and test them out. So why don't you do that? Why don't you pause the video for just a minute, test out these numbers, and tell me what signs they generate. All right, so hopefully you ran these numbers through your first derivative. I got negative, positive, negative, negative. So that means that this is decreasing, increasing, decreasing, decreasing. So if I'm going from decreasing to increasing, I can conclude that 0 is a local min for my function. And if I'm going from increasing to decreasing, I can conclude that 4 is a local maximum. All right, so that is the first half of my information. And I'm going to go back to this information when I'm ready, but I would like to do my second derivative test in an effort to get more information. All right, so I'm going to kind of box this off and say that that information I need to come back to. All right, so my second derivative test. Now, let's remember what our second derivative was, f double prime of x equals, I'm going to rewrite it simply because I don't want to scroll back and forth. To the 5/3. Okay. So now the first thing we need is our points of inflection. I'm going to use POI, right, as an abbreviation for points of inflection. It's readily accepted. All right, now let's look at our second derivative. Is there any place where the second derivative is going to equal 0? All right, if there is, right, our numerator we set equal to 0 and solve. So I conclude that there's no place where the second derivative is going to equal 0 because our numerator is just -8, and -8 will never equal 0. So we only need to look for where our second derivative is undefined, and it's undefined at x equals 0 and x equals 6. All right, so those are the only two possible points of inflection. I say possible because if the concavity, again, does not change, we can't count it as a point of inflection. All right, so let's make our chart again. All right. So our interval goes from -infinity up to 0. Then from 0 to 6. Then from 6 to infinity. All right, -1, 1, and 7. I don't get much points for originality, but again, these points I'm picking are just for ease of plugging in. So why don't you do this at this point? Let's stop the video, and why don't you plug these into our second derivative. I'll scroll up a little bit. There it is. And we'll talk about what I got on the back end. All right, hopefully you paused the video and did the math. I got negative, negative, positive. Again, I don't care what the number is. I just care whether the number is negative or positive. So this is concave down, this is concave down, and this is concave up. All right, so again, concavity doesn't have to change, but these are the only possible points where it could change. All right, so 0 is not a possible point of inflection. but 6 is an x value that will be a possible point of inflection. All right. Now you get the y value by plugging into the original function. All right. So let's scroll up for just a second. Let's see if we can find that original function again. It's been a while. That's not it. Here it is. Here's our original function. If we plug 6 in, 6 minus 6 is 0. The whole thing is going to equal 0. So my y value on 6 would be 0. All right. So this is our point of inflection. Or the concavity is going to indeed change. All right, so let's see what kind of information that we have, and then we can write some stuff down. So if I go back, if I scroll up to my first derivative test, I see that I'm decreasing to 0. Then between 0 and 4, I'm increasing. All right, so I'm just going to write this down. Right? This writing it down isn't part of my answer necessarily. Right now, I really just want a graph, or a sketch of a graph. But if I'm going to keep scrolling up and scrolling down, it's going to drive me nuts. So basically what I want to do is I just want to take what I need to know out of my earlier notes and organize it. So between 4 and 6, I'm going down, and 6 and infinity, I'm going down. So 4. All right, so from 4 to infinity, I am decreasing. All right. Now for my concavity, all right, for concavity. So this is my first piece of information. For my second piece for my concavity, I'm concave down to 0. Then between 0 and 6, I'm concave down. So I'm concave down, right, to 0. Then stay down to 6. All right. And then from I can do better than that. From 6 to infinity, I'm concave up. All right, so let's see if I can sketch a graph that kind of takes all this stuff into account. All right, let's see what I can do. So from negative infinity to 0, I'm concave down. All right, now I'm going to have a corner there because if we look, we notice that, let's see, let's go back to the original, right? 0 makes 0, and our first derivative at 0 is undefined, right? If our first derivative at 0 is undefined, but it's a continuous function, there must be a corner there. All right? Now, I'm going to go 1, 2, 3, 4, 1, 2, 3, right? At 4, what is my value? So what I can do is I can say, I need to know what value that is. All right, so if I plug 4 into my original, all right, let's see what I get. I get 6 minus 4 is 2, 2 to the 1/3. I'm pretty close to 3, right? So I'm going to kind of go just a little bit below 3. So I'm kind of right there. Now remember, I've got to be concave down, right? All the way to 6. And then at 6, even though it's still, right? Still decreasing, but concave up. So I'm going to be still decreasing, but concave up. So my graph is going to look something like this. Again, you're not going to get an exact graph. You're just going to do an estimate. All I'm looking for is a good sketch. I want your picture to look very similar to my picture. All right, and I want you to be able to show me that you're using the information and applying it to the graph of the function. That's the big deal here, all right? So the first thing to do is organize your work, do all of the first derivative test, then do all of the second derivative test. Then gather the information you learned from each one of those two tests and make a graph. The more organized your work is, the more likely I'll be able to read it easier. All right, guys, I'm not going to keep you too much longer. Thanks for listening, and I look forward to seeing you guys next time. Have a good one.